Assalamu alaikum. I am Sadda Fayat from MS Chemistry. I am a student of UMT Sialkot. Today I am here to present a topic triamino trinitrobenzene. Here are some outlines which will cover in this video. First of all, like its introduction, chemical identity, structure and bonding, its physical properties, chemical properties, method of preparation, its applications, advantages and disadvantages. In its introduction, we will cover that triamino trinitrobenzene, which is an important, insensitive, high explosive material. Unlike its conventional explosives, it's combine high explosive performance with exceptional safety. It is extremely resistant to heat, shock, friction, and impact, which make it valuable in applications where accidental detonation must be avoided. Because of these unique properties, this material is mainly used in defense nuclear technology rather than civilian industries. Here are some its chemical identity, like its chemical name, its molecular formula, molecular weight. There are two functional groups which are present in this material, like triamino group and three nitro groups. This molecule is based on benzene ring, where amino and nitro groups alternate in symmetrical pattern. This balanced substitution plays a major role in its stability, its structure and bonding. This material has highly symmetrical aromatic structure. The benzene ring provides rigidity, while the amino group and nitro group indicate interact strongly with each other. A key feature is strong intermolecular and intramolecular hydrogen bonding between amino and nitro group. These hydrogen bonds which are present in these groups basically reduce molecular mobility, absorb its mechanical energy, prevent rapid bond breakage. As a result, this material does not donate easily under mechanical stress. Here are some physical properties, like its appearance. It looks like yellow crystalline solid. Its density is 1.93 gram per centimeter cube. Its melting behavior does not melt normally, decompose at very high temperature like 350 degrees Celsius. Solubility insoluble in water and most organic solvents. The low solubility and high decomposition at high temperature indicate that the strong crystalline force present between these molecules. Chemical properties. Chemically, this material is remarkably stable compared to other nitro explosive, resistant to oxidation, reduction under normal conditions, shows low reactivity toward acid and base, does not easily undergo normal thermal decompositions. The presence of both electron donating and electron withdrawing groups balance the electron density in aromatic ring, making the compound usually stable. Synthesis of triamino trinitrobenzene. Here are a theoretical step out synthesis pathway in which we will discuss the synthesis of this material in detail. The synthesis of this material is a classic example of multi-step organic chemistry involving like electrophilic aromatic substitution followed by the nucleophilic aromatic substitution. Here is a theoretical synthesis pathway. The production of this material typically start from a 1,3 trinitro chlorobenzene, because the chlorine atoms serve as an excellent placeholder and leaving group for the final amino group. Step 1 is nitration. In this stage, the benzene ring is packed with a nitro group. Reagent which are used are mixture of concentrated nitric acid and sulfuric acid. Process. The trichlorobenzene undergo nitration at high temperature, approximately 150 degrees Celsius. Result: these produce 135 trichloro 2,4 trinitrobenzene. The three chlorine atom are orthopara directing because they are located at position 1, 3 and 5 at the nitro group. naturally gravitated to the empty 2, 4, and 6 positions, creating a perfectly symmetrical, fully substituted benzene ring. Here is one step is complete in which the 135 trichloro 246 trinitrobenzene is synthesized. In step 2, amination will be occur. The chlorine atom must now be replaced with amino group. Reagent which are used are non-hydrous ammonia or toluene, solution of ammonia. The reaction is carried out in a pressurized vessel at temperature around 150 degrees Celsius, which is a high temperature. Result: the chlorine atom are displaced by the ammonia, yielding this material and hydrogen chloride gas as a byproduct. Byproduct is basically one thing which is a hydrogen chloride chemical. This is nucleophilic aromatic substitution reaction. Normally benzene does not like nucleophiles because it is electron rich. However, these three nitro groups are extremely electron withdrawing. They pull electron density away from the ring, making the carbon atom attached to the chlorine very thirsty for electrons, allowing the ammonia to attack and bond. Here is a chemical mechanism which will you can see either the first step is nitration, where is 135 trichloro 246 trinitrobenzene benzene is synthesized. In step 2, you can see that there is a nucleophilic aromatic substitution, and at the end this material is synthesized. A relation of this material with artificially intelligence, like here we will discuss about the chemistry with this material compare with the other sciences like AI, medical engineering. First of all, we will discuss the this material with the AI. Material is a model compound for studying structure, stability, relationship. AI algorithms are used to predict thermal stability of energetics material, model electron density distribution, optimize molecular symmetry and hydrogen bonding. This material is used to train AI models that predict super high energy material without place physical testing. AI in safety and risk analysis, because this material is the insensitive explosive. It is used as a benchmark in machine learning, safety, predictive failure analysis, impact and shock response modeling. Relation of this material with medical engineering, same as it design material that must absorb shock, a resistant sudden energy release, remain stable under stress. These material will be synthesized by this material protective coating for medical devices, shock resistant, safe housing for sensitive diagnostic materials, hydrogen bonding and drug design. This material is an excellent academic example, like hydrogen strong bonding, molecular rigidity, crystallic stability, drug stability, control release, pharmaceuticals, protein ligand interaction modeling. Now this we will discuss about the relationship of this material with science and engineering. This material demonstrate distance, dense crystal packing, strong intermolecular force, high thermal stability, advanced ceramics, high temperature polymers, insensitive material design, battery safety system, pressure resistant composites, high resistance coating. Relationship of material with physics, solid state physics, lattice vibration, thermal conductivity behavior. These studies help करता है, for example designing vibration, improving thermal shielding, energy transfer mechanisms, absorb energy internally, prevent rapid bond rupture, shock wave physics, protective material design. Now here is a relation of material with chemistry. aromatic substitution effects, electron donating withdrawing groups, sorry, resonance stabilization, physical chemistry, high activation energy, reaction kinetics, thermodynamic stability, relation of material with environmental science. It control to study in waste management modeling, long term material persistence analysis. Environmental scientists study material to understand how stable compound behave over decades. Now there is a relation of this material with the defense engineering. Although military in origin, the science behind this material sports, spacecraft safety material, rocket insulation material, high reliability component in extreme environments. Here are some applications of this material, like nuclear weapon safety. The golden application is a nuclear weapon. A conventional high explosive is used to compress the fissile core to trigger a nuclear chain reaction. The risk: traditionally explosives like TNT and RDX could detonate accidentally if a plane crash, a fire breaks out, or the weapon is struck by a bullet or sparnel. The tab solution tab is so stable that is virtually impossible to net by accident. It can be hit with a hammer dropped from the great height, or even engulfed in a jet fuel fire without exploding. It only donates when hit by a specific high velocity shockwave from a specialized donator. Here is an example. It is a thin ingredient in plastic bonded explosives like PBX 95240 and LX-17 used in B61 and B83 nuclear bombs. Deep oil and gas well exploration. This material is perfect tool for the oil industry where they're drilling into extreme environment. Its thermal shielding during atmospheric re-entry, spacecraft experience massive heat friction. This material is explosive bolts and separation stage because it can withstand the high shock material of re-entry without triggering prematurely. Here is the abstract of this whole material which we discuss above in this video. And at the end there are the some references which are from which this material are extracted. Hope so you will be understand this material, its synthesis, its physical and chemical properties, its introductions, and thank you.